Look up at the night sky. It feels open, endless and free. The stars seem scattered across an infinite emptiness, and the universe appears to stretch outward with no boundaries at all. But this sense of openness may be one of the greatest illusions ever experienced by humanity. There is a possibility grounded in real physics that challenges everything we think we know about reality. A possibility so extreme that it forces us to question not only where the universe came from, but where it exists. The idea is simple to state, yet deeply unsettling. The entire observable universe, every galaxy, every star, every planet, and every particle that makes up your body could exist inside a black hole. This does not mean the universe is collapsing or being destroyed. It means the structure of reality itself may be radically different from how it appears. Space may not be expanding into nothing. It may be expanding inside something. At first glance, this sounds impossible. Black holes are associated with destruction, darkness, and violent collapse. The universe, by contrast, is ancient, structured, and filled with light. These two ideas seem fundamentally incompatible, but modern physics has a long history of overturning intuition. Time slows near massive objects. Space bends. Particles exist in multiple states at once. The deeper we explore the equations that govern reality, the less reality resembles common sense. This idea does not come from imagination. It emerges from mathematics, from the same equations that accurately describe gravity, stars, and the evolution of the cosmos. This is not a claim or a conclusion. It is a question, one that refuses to go away. Because if this possibility turns out to be real, it would not merely change our understanding of the universe. It would be the most profound and mind-altering discovery in human history. The idea that the universe might exist inside a black hole immediately raises a deeper question. If this is true, then the Big Bang may not have been the true beginning of everything. For more than a century, the Big Bang has stood as the starting point of cosmic history. When astronomers rewind the expansion of the universe backward in time, all matter, energy, space, and even time itself converge toward a single moment. That moment is described as the birth of the universe. But when physics reaches that point, something strange happens. The equations stop making sense. Density becomes infinite. Temperature becomes infinite. Space and time lose their meaning. This is not a description of creation. It is a description of failure. Our best theories collapse under their own weight. In science, this kind of breakdown is a warning sign. It tells us that the story is incomplete. Instead of asking what caused the Big Bang, physicists began asking a more unsettling question. What if the Big Bang was not the start of time, but a transition? What if it marked the moment when space-time emerged from an extreme state, rather than coming from nothing at all? This idea changes the role of the Big Bang completely. It transforms it from a beginning into an event. Something physical, something that happened within a larger structure. If the universe truly exists inside a black hole, then the Big Bang could represent the interior response to gravitational collapse elsewhere. From the inside, space expands. From the outside, matter falls inward. Two perspectives of the same process. This possibility does not answer every question, but it reframes them. And once the Big Bang is no longer treated as the absolute beginning, the door opens to a far darker and far stranger explanation of reality itself. Once the Big Bang is no longer treated as an absolute beginning, the next question becomes unavoidable. If it was a transition, then a transition from what? To answer that, physicists turn to the deepest equations we have. Einstein's equations of general relativity describe how mass and energy shape space-time, and they have passed every experimental test ever thrown at them. They predict how planets move, how stars evolve, and how galaxies form. They also predict something far more disturbing. When massive stars collapse under their own gravity, these equations lead to black holes, regions where space-time curves so extremely that nothing can escape. At their center lies a singularity, a point where density becomes infinite and the laws of physics cease to function. Now comes the unsettling part. When those same equations are used to describe the early universe, they produce the same result. As the universe is traced backward in time, density increases without limit. Space-time curvature explodes. Once again, physics breaks. Two completely different scenarios, one involving a dying star, the other involving the entire universe. Yet mathematically, they end the same way. This is not coincidence. In physics, identical mathematical behavior usually signals identical underlying structure. It suggests that these two events, collapse and expansion, are deeply connected. In both cases, classical physics reaches a boundary it cannot cross, not because reality ends there, but because our descriptions do. This realization changed the conversation. Instead of treating singularities as physical points, many physicists began to view them as signs that space-time itself undergoes a transformation. A phase change, similar to water freezing into ice or boiling into vapor. If that is true, then the Big Bang singularity may not represent creation from nothing. It may represent the moment space-time reorganized itself into a new form. And if space-time can transform under extreme gravity, then the interior of a black hole is no longer a dead end. It becomes a candidate for something far more radical, a birthplace. As the connection between black holes and the early universe becomes harder to ignore, attention turns to the place where both descriptions fail. In both cases, that failure occurs at a singularity. A singularity is not an object in the usual sense. It is a breakdown, a region where density grows without limit, distances collapse, and the equations that normally describe space and time stop giving answers. Cause and effect lose their familiar meaning. Inside a black hole, this breakdown is hidden deep within. The singularity sits at the center, completely isolated from the rest of the universe by an event horizon. Once that boundary is crossed, no information can return. Whatever occurs at the singularity is forever inaccessible to an outside observer. When cosmologists examine the universe's earliest moments, they encounter the same kind of boundary. Tracing the expansion backward leads to a state where all matter and energy converge into an extremely compact configuration. Space itself shrinks towards zero size. Time, as we understand it, ceases to behave normally. Once again, the equations signal that they can go no further. This parallel forces a shift in interpretation. Rather than viewing singularities as literal points of infinite density, many physicists treat them as indicators that a deeper description of reality is required. They mark the limits of classical space-time, not necessarily the limits of existence. If space-time can emerge and transform under extreme conditions, then the singularity inside a black hole may not represent an ultimate end. Likewise, the singularity associated with the Big Bang may not represent an absolute beginning. Instead, both may describe a passage between phases of space-time itself. From one side, matter collapses inward under gravity. From the other, space unfolds and expands. Seen this way, black holes and the early universe are no longer isolated mysteries. They become connected stages of the same underlying process. And that connection reshapes how we think about the most extreme places in the cosmos. If singularities mark the limits of our understanding, horizons define the limits of what can ever be known. In a black hole, the event horizon is not a physical surface. Nothing special happens when it is crossed. There is no wall, no sudden force. And yet it represents a one-way boundary in space-time. Once something passes beyond it, no signal it sends can ever reach the outside universe again. Information is not destroyed, but it is permanently hidden. This concept changed how physicists think about space and causality. It showed that reality can contain regions that exist, but can never be observed or influenced from the outside. Then cosmologists noticed something unsettling. Our universe has a horizon too. Because light travels at a finite speed and the universe has a finite age, there is a limit to how far we can see. This boundary is known as the particle horizon. It marks the most distant regions of space whose light has had time to reach us since the universe began expanding. Beyond that boundary, the universe may continue, but it is causally disconnected from us. No signal from there can ever arrive. No observation can ever be made. Functionally, this cosmic horizon behaves in the same way as a black hole's event horizon. both separate spacetime into regions that can exchange information and regions that cannot. Both define what is observable and what is forever hidden. And in both cases, the boundary is not about distance, but about time and causality. This parallel introduces a powerful idea. From our perspective inside the universe, the particle horizon feels like a natural observational limit, but from another perspective, it could be something more. If the universe formed within a black hole, then this horizon would not simply be a consequence of cosmic expansion. It would be the event horizon of the black hole itself, seen from the inside. In that picture, the reason we cannot see beyond the edge of the observable universe is not because nothing exists there, but because spacetime forbids any connection. The universe would not be unbounded, it would be enclosed, and the structure defined by singularities and horizons together would begin to resemble something very specific. Not an explosion into emptiness, but the interior geometry of a black hole. By this point, the similarities between black holes and the observable universe are no longer abstract. Singularities define their deepest limits, horizons define what can be known. But there is one more step where the comparison becomes impossible to ignore. It is where the mathematics stops being suggestive and starts being precise. A black hole's event horizon has a well-defined size. It depends only on one thing: mass. The more mass a black hole contains, the larger its horizon becomes. This relationship is simple, exact, and derived directly from Einstein's equations. Cosmologists know how much matter and energy exist inside the observable universe. Galaxies, stars, gas, dark matter, all of it contributes to the total mass. This value is not guessed, it is measured. When physicists took the black hole horizon equation and substituted the mass of the observable universe into it, they did not expect anything remarkable to happen. Something did. The resulting horizon radius matched the size of the observable universe itself. Not approximately, not within vague margins. The scale defined by cosmic expansion and the scale defined by gravitational collapse turned out to be the same. This result does not prove that the universe is a black hole, but it removes coincidence as an easy explanation. Two completely different physical contexts, governed by the same equations, produce the same boundary. This forces a difficult question. If the observable universe has the size it would have if it were a black hole of its own mass, then what exactly is that boundary? Within standard cosmology, it is treated as a limit imposed by time and expansion, but the mathematics allows another interpretation, one in which the boundary is not accidental but structural. In that interpretation, the observable universe is not simply a region we happen to see. It is the interior of a space-time configuration defined by gravity. From the inside, space expands, distances grow, galaxies drift apart. From the outside, mass collapses inward. The same equations describe both views. At this stage, the idea stops sounding like metaphor. It becomes a legitimate physical possibility. And once that possibility is taken seriously, the universe begins to look less like an explosion into emptiness, and more like something shaped, bounded, and born inside something else. Once the mathematical parallels could no longer be ignored, physicists began asking a question that would have sounded absurd only decades earlier. If the universe behaves like the interior of a black hole, then what does that actually mean? This question gave rise to a framework known as black hole cosmology. Rather than treating black holes as endpoints where physics simply fails, this approach treats them as regions where space-time continues in a radically different form. From the outside, a black hole appears frozen. Matter falls inward and seems to slow, never quite crossing the event horizon. But this is an illusion created by perspective. For anything falling inside, the horizon is crossed in finite time, and space-time continues beyond it. According to black hole cosmology, what happens next is not destruction, but transformation. Inside the horizon, the roles of space and time begin to blur. The direction that once pointed inward becomes unavoidable, just as the future is unavoidable in normal space-time. Movement toward the singularity is not motion through space, but motion through time. In this extreme environment, space-time itself may reorganize. Instead of ending, it may expand. This is where the concept of a white hole enters the picture. A white hole is the time-reversed counterpart of a black hole. Nothing can enter it. Everything must exit. In theory, it is a region where matter and energy are expelled rather than consumed. If a new region of space-time were to emerge from within a black hole, it would look like a white hole from the inside. Space would expand rapidly. Matter would stream outward. From within that region, the expansion would appear uniform and all-encompassing. This description closely mirrors what we observe when we look back toward the earliest moments of our universe. In this framework, the Big Bang is no longer an inexplicable beginning. It becomes a natural consequence of gravity pushed to its extreme limits. Our universe would not be unique or isolated. It would be the interior continuation of a gravitational collapse that occurred elsewhere. And the black hole that gave rise to it would not be visible to us at all, because its event horizon would be our entire observable universe. Up to this point, the idea that our universe could exist inside a black hole has rested on theory and mathematics. Elegant, consistent, but indirect. For decades, it remained a possibility without an observational foothold. That changed when astronomers began looking deeper into the universe than ever before. Modern cosmology is built on a foundational assumption known as the cosmological principle. It states that, on the largest scales, the universe should look the same in every direction. No preferred orientation, no global structure, no cosmic bias. This assumption is not philosophical. It is practical. Every major model of the universe depends on it. If the universe truly has no preferred direction, then patterns such as galaxy rotation should be evenly distributed. For every spiral galaxy rotating one way, there should be another rotating the opposite way. This expectation held for decades. Then the James Webb Space Telescope began delivering its first deep-field observations. In a recent analysis, researchers examined hundreds of distant spiral galaxies located billions of light-years away. These galaxies were not nearby mature systems. They were ancient, seen as they existed when the universe was much younger. What the researchers found was unexpected. Instead of an even split, a strong imbalance appeared. Roughly 2/3 of the galaxies rotated in the same direction, while only 1/3 rotated the opposite way. If confirmed, this asymmetry should not exist. Such a pattern suggests a preferred axis, a large-scale orientation imprinted on the universe itself. Standard cosmology offers no clear mechanism for creating this effect, but within the framework of black hole cosmology it takes on new meaning. If the universe formed inside a black hole, then it would inherit properties from that black hole. And black holes are not static objects. They can rotate. A rotating black hole drags space-time around with it, imprinting a global direction onto everything inside. Matter forming later would not start from randomness alone. It would remember that motion. For the first time, a theoretical idea encountered a possible observational echo. The universe may not be as directionless as we believed. And that realization forces us to reconsider whether what we are seeing is merely cosmic chance, or the first visible scar left by the black hole that contains us. The unexpected rotation pattern seen in distant galaxies raises an obvious question. If the universe does have a preferred direction, where could it have come from? To answer that, we need to understand an often overlooked fact about black holes. Most black holes do not sit still. When massive stars collapse, they almost always carry some rotation with them. Conservation of angular momentum ensures that as matter collapses inward, it spins faster. The result is a rotating black hole known as a Kerr black hole. Unlike non-rotating black holes, Kerr black holes profoundly affect the structure of space-time around them. Their rotation drags space-time itself into motion, twisting it in the direction of the spin. This effect, called frame dragging, is not speculative. It has been measured around Earth and observed near black holes. Inside a rotating black hole, this effect becomes extreme. Space-time no longer allows stillness. Every possible path forward is influenced by the rotation. There is a preferred axis built directly into the geometry of reality. If our universe formed within such a system, this rotation would not vanish. It would be inherited. Matter emerging into an expanding spacetime would carry subtle traces of that original motion. Over billions of years, as matter cooled and galaxies formed, that inherited preference could reveal itself as a statistical imbalance, not in individual galaxies, but across vast cosmic scales. This provides a natural explanation for why many distant galaxies appear to rotate in the same direction. They would not be randomly oriented remnants of chaos. They would be descendants of a spacetime that was already spinning. There is another crucial consequence of rotation. In non-rotating black holes, the singularity is a point. In rotating black holes, it is not. The singularity stretches into a ring. That change may seem technical, but it carries profound implications. A ring singularity alters the internal structure of the black hole, allowing paths through spacetime that do not end in destruction. In theory, this opens the possibility for spacetime to pass through the black hole rather than terminate inside it. If such a passage exists, the emergence of a new expanding region would look exactly like what we call the Big Bang. Not an explosion into nothing, but an expansion driven by rotation, geometry, and gravity. And if that is true, then the spin seen in distant galaxies may be more than an anomaly. It may be a memory. A faint, ancient trace of the black hole that gave birth to the universe itself. If the universe truly emerged from within a rotating black hole, then the implications extend far beyond cosmology. They reshape how we think about reality itself. First, the scale becomes almost impossible to grasp. For the observable universe to fit within a black hole, that black hole would have to be unimaginably massive. Trillions upon trillions of times the mass of the Sun. Its event horizon would span billions of light years. Compared to it, even the largest black holes we observe today would be microscopic. From the inside, however, none of this would feel extreme. Space would expand smoothly. Galaxies would drift apart. Physics would behave exactly as we observe it to behave. The event horizon would not appear as a wall, but as the natural limit of what can ever be seen. This idea also changes how we think about cosmic origins. If black holes can give rise to new universes, then our universe is not unique. Every sufficiently massive black hole could contain its own interior cosmos, unfolding according to the same physical laws. Those universes could, in turn, produce black holes of their own. The result is a nested structure of reality. Universes inside black holes inside universes, repeating across scales. In such a picture, survival takes on a new meaning. Universes that are better at forming black holes create more offspring. Over immense timescales, this could act as a form of cosmic selection, shaping the fundamental constants of physics themselves. But this is where restraint becomes essential. The observational evidence is still limited. The galaxy rotation data comes from a small patch of the sky. Subtle biases in observation, instrumentation, or data processing could mimic the effect. Similar claims in the past have faded under closer scrutiny. Science does not move forward by dramatic ideas alone. It moves forward by doubt, repetition, and verification. Yet, the possibility remains. The equations allow it. The structure supports it. And the universe may be offering hints that something deeper is at work. If future observations confirm these patterns, the conclusion would be unavoidable. The Big Bang would not mark the beginning of everything. It would mark the moment our universe emerged from the depths of a black hole, and humanity would discover that we are not simply living in the universe. We are living inside one of the darkest objects nature can create.